databasehomeworkhelp.com info@databasehomeworkhelp.com or reach us at https://www.databasehomeworkhelp.com. https://www.databasehomeworkhelp.com. Database Management System Homework Help. Version History. In this lab, you will implement a query optimizer on top of SimpleDB. The main tasks include implementing a selectivity estimation framework and a cost-based optimizer. You have freedom as to exactly what you implement, but we recommend using something similar to the Sellinger cost-based optimizer discussed in class. The remainder of this document describes what is involved in adding optimizer support and provides a basic outline of how you might add this support to your database. As with the previous lab, we recommend that you start as early as possible. Locking in transactions can be quite tricky to debug. 1. Find bugs, be patient, earn candy bars. It is very possible you are going to find bugs, inconsistencies, and bad, outdated, or incorrect documentation, etc. We apologize profusely. We did our best, but, alas, we are fallible human beings. We ask you, therefore, to do this lab with an adventurous mindset. Don't get mad if something is not clear, or even wrong, rather, try to figure it out yourself or send us a friendly email. We promise to help out by sending bug fixes, new tarballs, etc. And if you find a bug in our code, we'll give you a candy bar, see section 3.3. databasehomeworkhelp.com. 1. Getting started. You should begin with the code you submitted for Lab 3. If you did not submit code for Lab 3, or your solution didn't work properly, contact us to discuss options. We have provided you with extra test cases, as well as source code files for this lab that are not in the original code distribution you received. We reiterate that the unit tests we provide are to help guide your implementation along, but they are not intended to be comprehensive or to establish correctness. You will need to add these new test cases to your release. The easiest way to do this is to untar the new code in the same directory as your top-level simple directory, as follows. Make a backup of your Lab 3 solution by typing. Rename the directory that contains the code. Download the new tests and skeleton code for Lab 4 from http://db.csail.mit.edu/6.830/6.830-lab4-supplement. tar.gz $get http://db.csail.mit.edu/6.830/lab4-supplement.tar.gz. Extract the new files for Lab 4 by typing tar xvzf 6.830 lab4supplement.tar.gz. databasehomeworkhelp.com. The following files are modified, and the tar command should overwrite them in your Lab 4 directory, src/parser.java src/simpleb/simpledb.java src/simpleb/utility.java test/systemtest/systemtestutil.java. Note that the changes include a new simpledb.java file under src/simpleb. The modified parser.java refers to this simpledb.java. It's safe to delete src/simpledb.java. If you have modified either of these files, you should be able to simply install our new version, though you may wish to double-check with us before doing so. 2. Optimizer outline. Recall that the main idea of a cost-based optimizer is to use statistics about tables to estimate costs of different query plans. Typically, the cost of a plan is related to the of cardinalities, number of tuples produced by, intermediate joins and selections, as well as the selectivity of selection and join predicates. Use these statistics to order joins and selections in an optimal way, and to select the best implementation for join algorithms from amongst several alternatives. In this lab, you will implement code to perform both of these functions. The optimizer will be invoked from simpleb/parser.java. You may wish to review the Lab 2 parser exercise before starting this lab briefly. If you have a catalog file catalog.txt describing your tables, you can run the parser by typing, from the simple /directory, Java class path bin/src/ lib/line 0.9.94.jar, lib/sql4j.jar, lib/zql.jar simple parser catalog.txt. Note that this method of invocation is slightly different from that given in Lab 2 because we inadvertently distributed a simple.java class that lacked the parser option. If you made the method in Lab 2 work, you may run the parser in that way as well. Databasehomeworkhelp.com. When the parser is invoked, it will compute statistics over all of the tables, using statistics code you provide. When a query is issued, the parser will convert the query into a logical plan representation, and then call your query optimizer to generate an optimal plan. The overall control flow of the SimpleDB modules of the parser and optimizer is shown in Figure 1. The key at the bottom explains the symbols. You will implement the components with double borders. The classes and methods will be explained in more detail in the text that follows. You may wish to refer back to this diagram, but the basic operation is as follows. 1.parser.java constructs a set of table statistics, the table stats map, when it is initialized. It then waits for a query to be input and calls parseQuery on that query. ParseQuery constructs a logical plan that represents the parsed query. 2.parseQuery calls physicalPlan on the logical plan it has constructed. PhysicalPlan will return a DB iterator object that can be used to actually run the query. You will implement the methods that help PhysicalPlan devise an optimal plan. In particular, you must write the methods in tablestats that allow it to estimate the selectivities of selections and the cost of scans using histograms, the int histogram class, or some other form of statistics of your devising. PhysicalPlan constructs a map called filter selectivities using these methods to estimate the selectivities of the filter expressions over all the tables. Databasehomeworkhelp.com. Databasehomeworkhelp.com. You must write the methods in Join Optimizer that allow it to estimate the cost and selectivities of joins. You must write the orderJoins method that produces an optimal ordering for a series of joins, likely using the Selinger algorithm studied in class, given the filter selectivities and table stats objects computed in prior steps. Figure 1. Diagram illustrating classes, methods, and objects used in the parser and optimizer. 1. Statistics estimation. Accurately estimating plan cost is quite tricky. In this lab, we will focus only on the cost of sequences of joins and base table accesses. We won't worry about access method selection, since we only have one access method, table scans, or the costs of additional operators, like aggregates. You are only required to consider left-deep plans for this lab. See Section 2.3 for a description of additional bonus optimizer features you might implement, including an approach for handling bushy plans. Databasehomeworkhelp.com. Scan cost, T1, plus scan cost, T2, plus join cost, T1 join T2, plus scan cost, T3, plus join cost, T1 join T2, join T3, plus. Here, scan cost, T1, is the I/O cost of scanning table T1, join cost, T1, T2, is the CPU cost to join T1 to T2. To make I/O and CPU cost comparable, typically a constant scaling factor is used, e.g. cost, predicate application, equals 1 cost, page scan, equals scaling underscore factor x cost, predicate application. 1. Overall plan cost. We will write join plans of the form P equals T1 join T2 join, Tn, which signifies a left deep join where T1 is the leftmost join, deepest in the tree. Given a plan like P, its cost can be expressed as. For this lab, you can ignore the effects of caching. Example, assume that every access to a table